You have probably heard it repeated 1,000 times. Pound for pound, spider silk is 5 times stronger than steel. It sounds like an exaggeration, the kind of pop science trivia that gets passed around until everyone just accepts it as fact. After all, structural steel holds up 60-story skyscrapers, while a spider web gets wiped away by an accidental brush of your hand. So what actually happens when you take those claims out of the textbook and load them onto a tensile test rig in a materials lab? When you clamp a single strand of dragline spider silk into a micro-tensile tester, the machine pulls it at a steady, measurable rate until it breaks. The live data curve on the monitor tells a story that human metallurgy has been chasing for decades. Steel is stiff and remarkably strong, but it is heavy, and under sudden dynamic shock, it can fail catastrophically. Spider silk possesses something much rarer: extreme toughness. In materials science, toughness does not just mean resisting a scratch or holding a static load. It measures how much raw energy a material can absorb before snapping. When a flying insect hits an orb web at full speed, the web cannot be rigid like metal wire. If it were, the sudden kinetic shock would snap the anchor points instantly. Instead, the silk deforms, stretching up to 40% of its original length while dissipating that violent energy as heat. Under an electron microscope, the secret becomes clear. Spider silk is not a uniform synthetic filament. It is a hierarchical composite built from complex proteins. Tiny, rigid crystalline blocks called beta sheets provide raw tensile strength, while loose, disordered protein chains between them act like coiled springs. As tension increases, those flexible chains uncoil one by one, absorbing massive energy before the crystalline core ever takes the strain. So why aren't we building suspension bridges and airplane wings out of bioengineered silk? Because biological materials come with brutal trade-offs. In a controlled lab test, the moment you introduce moisture, heat, or sustained load, the illusion of perfection begins to crack. Add water, and spider silk undergoes supercontraction. The internal hydrogen bonds reorganize, causing the fiber to shrink and lose its tension. Leave it exposed to harsh outdoor ultraviolet radiation, and the organic polymer chains degrade in weeks. Steel might oxidize over time, but it does not collapse into a limp strand of protein when it rains. Spider silk is not the only natural material outperforming our best engineering. Look at nacre, the iridescent mother-of-pearl lining inside an abalone shell. Chemically, it is 95% calcium carbonate, essentially brittle mineral chalk. Yet nacre is 3,000 times tougher than the mineral alone. Nature arranges it into a microscopic brick-and-mortar pattern, sandwiching mineral tiles between elastic biopolymers. When a crack starts, it cannot travel straight through. It gets diverted into a labyrinth of microscopic dead ends, bleeding off force until it stops. Human engineering has spent centuries mastering brute force, smelting metals at thousands of degrees, synthesizing rigid plastics, and maximizing static hardness. But nature manufactures at room temperature, using weak, abundant ingredients and solving mechanical problems with geometry. Natural structures do not beat human materials because they are unbreakable. They beat them because they are designed to fail gracefully. And as we continue to test these biological structures to their absolute breaking point, the real breakthrough will not be replacing steel with silk, but learning how to build our own materials with nature's architecture.